Welcome back. In our last video, we concluded our first hypothesis test, specifically a one-sample z-test for a population proportion. And the next few videos are going to go step by step through two additional examples where we'll have completely new scenarios and we'll actually go back to calculating confidence intervals and doing hypothesis tests for those new examples. And we'll see a couple new things pop up that we weren't able to get through the first time we did those things. But before we get to the examples, I wanted to talk a little bit more about p-values and what they mean. We've already talked about how to interpret them, but just looking at them from a different angle. So in this puffy cloud, we see something we are familiar with from the last video. The entire point of the hypothesis test, the central idea, is that you want to compare your p-value, which measures how likely or unlikely your sample result is, if the null hypothesis is true, to some previously determined significance level, alpha. If your p-value is less than alpha, then we reject the null hypothesis, and we conclude that there's evidence of whatever the alternative hypothesis says. This is what happened in our first hypothesis test example. We determined that since the p-value was less than alpha, we rejected the null hypothesis and concluded that the true proportion of adult Hoosiers that know who the president is greater than what we thought it was originally, the 90%. If instead the p-value is bigger than alpha, then we fail to reject the null hypothesis and conclude that we don't have evidence of the alternative hypothesis. Now, I'm not a huge fan of these absolute terms like either there is evidence of the alternative or there is not evidence of the alternative. It's nice to be able to break it down into something binary like that, but the truth is a little more gray than black and white. Okay? This will serve you well if you know that. Knowing what it means to reject the null hypothesis, what it means to fail to reject. But in truth, in general, the smaller the p-value of a test is, the more convincing evidence your sample is providing against the null hypothesis and in favor of the alternative. So in the example that we did for our hypothesis test, our p-value was 0.0038, which was less than 0.05. That was our significance level alpha. Since our p-value was less than that, we rejected the null hypothesis. Let's say we took a different sample from the same population, another sample of 400 Hoosiers, and that time we get a p-value of 0.047. Okay. If we're still going to compare it to 0.05, the same significance level, the same alpha, that p-value is still less than alpha, which means we would still reject the null hypothesis. But these two p-values are quite different. If you recall our interpretation of the p-value, this one means that given that the null hypothesis is true, there's a 4.7% chance of getting a sample result at least as high as this one. Whereas the one we actually did, there was only a 0.38% chance of getting a sample proportion at least that high. So the smaller the p-value, the stronger evidence you have against the null hypothesis. We're still rejecting that null hypothesis for both of these samples. But the smaller that p-value is, the stronger the evidence is against that null hypothesis. So now we understand smaller p-values are more convincing evidence toward the alternative hypothesis away from the null. But what if the p-value is fairly large? What if it's like 0.5 or 0.6 or even higher than that potentially? Well, large p-values suggest only that your sample results are not particularly unusual, given that the null hypothesis is true. So if you've got a p-value of 0.6, let's say, that's fairly large. P-values can only go up to 1. A p-value of 0.6 means that if the null hypothesis is true, the chances of getting a sample result at least as extreme as yours is 60%. It's actually likely. Now, again, and I said this in the last video, but it's worth repeating. A large p-value is not evidence that the null hypothesis is true. We never want to make any statement about the null hypothesis being true because we don't know that. The null hypothesis is saying, well, at least for this type of test, that p is equal to a certain value. Taking a sample is not going to help us know that. This is why we say we fail to reject the null instead of saying we accept it. Large p-values are only saying, hey, our sample is not evidence of what we're trying to prove. We've got to just throw away our thoughts of that maybe this alternative hypothesis is true. If you get a large p-value, your sample's not that unusual, we fail to reject the null hypothesis. That's all you can really say. So hopefully that just shines a little more light on what it means to get certain p-values, giving a little more knowledge to how we conclude the test, what it is we are doing when we're performing a hypothesis test. It's more than just following directions. It actually allows you to say something that is meaningful outside of just a mathematical context. So, I want to go back to the start of the unit. We are going to come up with another example, fresh out the kitchen, and we're going to go through the entire process. We're going to calculate confidence interval, and we're going to perform a hypothesis test. This first example will be over the course of this video and the next one. We will then do yet another example in a video after that. Then you'll have enough material to work on the Chapter 19 homework in your next quiz. So let me get this next example up here and we'll get started. Okay, here's the beginning of our first example, and how this works is up to you. If you feel fairly confident that you've taken good notes and that you understand pretty well how to construct the sampling distribution, the confidence interval, and conduct a hypothesis test based on a scenario, you can do a lot of this on your own. Each part I will put up separately in this video, and I'll give you an opportunity to work on that part individually by yourself, and then we'll go over it. And then I'll put up the next part. You can work on it if you want to, and then we'll talk about it. If you're not ready to do it on your own yet, that's fine. I would encourage you, there will be a second example after this in a couple videos. I want you to work that one on your own when we get to that one. This will kind of be the last example that we could do together. Not necessarily me hand-holding you, but there will be some new things in here just to kind of catch up on some of the gaps. But if you want to work on this on your own and see how far you can get, see how well you can do, please do that. Okay? So, here we go. You take a large bag of M&Ms and notice that out of 122 M&Ms in the bag, 21 of them are orange. Assume M&Ms are distributed randomly into bags. Okay, so it appears we're interested in orange M&Ms here, and that's good because orange is the best color. Not just of M&Ms, just in general. Orange is the best color. Fight me. It totally is. So, that's all the information we have, I guess. What do we need to do here? Part A. Describe the sampling distribution of p hat, the sample proportion of orange M&Ms in a bag of 122 M&Ms. Check appropriate conditions. Now, on a quiz or a test or an AP test, this could be part A of a free response question, but generally, this is not explicitly asked for. Part A might be, go ahead and construct a confidence interval, or something like that. You need to know that if you are asked to construct a confidence interval or conduct a hypothesis test, either of those two statistical inference procedures, you need to do this first. You need to have a model for p hat to do either of those things. So you need to know what the model is, and in order to do that, you need to check the conditions so that you can use that model. So, if you want to try that out, go ahead and do that. Check the conditions first, then specify what the model is. If you want to do that, go ahead. If you want to do it together, let's get started. All right, let's get cracking here. We need to check the appropriate conditions so that we can use the model we want for p hat. And we should know that the sampling distribution of p hat, the model we want to use, we want to be able to say that it's approximately normal with a specific mean and standard deviation, just like before. So the conditions are the ones we usually check for one proportion. First one, we need randomization. Is this a random sample of M&Ms? Yes, it says assume M&Ms are distributed randomly into bags. So the randomization condition is met, so we'll write that down. I want to dispel a misconception that can be very harmful to believe. When it says to check the appropriate conditions, this is not testing whether you know what the conditions are. You can't, it would not do you well to just say randomization, check. 10% condition, check. Success failure, check. It's good that you know the names of the conditions, but you have to actually explain why they're met, right? So for the randomization condition, you can put randomization, M&Ms are distributed randomly into bags, but you need to not just maybe check appropriate conditions isn't what I should be saying there. You need to explain why each condition is met, not just list them and check them off, right? So you need to explain the randomization condition, not just put randomization check, right? The second condition is the 10% condition, which means we need to be sampling less than 10% of the population. Are we doing that? Well, our sample size is 122 M&Ms. Is that less than 10% of the population? I suppose the population is all M&Ms? I would like to think that there are more than 10 times this many out there. So, yes. The 10% condition, you may not know the population size, because honestly, I don't know if anyone knows how many M&Ms are in the world. People are constantly eating them, and they're constantly being made, so that number isn't really important. It's just that it's large. So to check the 10% condition, all you would have to say is something like 122 is less than 10% of all M&Ms. The last condition we need to check is success failure. And remember that's n times p and n times 1 minus p being at least 10. This is the condition that changes based on what it is you're trying to do. Now, you could try to keep it straight. Do you use p here? Do you use p hat? Do you use p naught from the null hypothesis? You could try to memorize those things, but think about what it is you know. Do you know p, the population proportion of orange M&Ms? No, that's not given here. Do you know p hat, the sample proportion of orange M&Ms? Yes, that's going to be 21 out of 122. Do you know what p naught or p0 is, the number in the null hypothesis? Well, no, because there aren't any hypotheses yet. We haven't been asked to do a hypothesis test. So, even though it's not clear what we're going to be doing in the rest of this problem yet, the only way we can check this condition is to use p hat for p, because we don't know p and we don't have a null hypothesis to work with. So we're just going to change these to p hats. And we're going to check to see if they're at least 10. N is our sample size. That's 122. P hat is 21 out of 122. And what's really nice about checking this condition with p hat, if all you have is the number of successes out of the total sample size, is that this becomes a very simple calculation. This is just 21. And that's bigger than 10, so we're good so far. N times 1 minus p. N is 122. And then this is going to be 1 minus 21 over 122. That can be a little nastier. That's essentially going to be the number of failures. So if you know the sample size is 122 and there are 21 successes, the rest are failures. The rest of the M&Ms are not orange. So there would be 101 of those. And if you type that into a calculator, you should get 101 there. That's also greater than 10. So that condition is also met. All of our conditions are met. So this is when we can say that the sampling distribution of p hat is approximately normal, right? That's what the success failure condition allows us to say. And we should also specify the mean and standard deviation of that sampling distribution. Since all of our conditions are met, the sampling distribution of p hat is approximately normal in shape. Remember, the success failure condition only allows us to say the sampling distribution is approximately normal. We'll never know whether it's actually normal, and in fact, that would be impossible. So always remember to put that approximately there. And it might help also if we want to describe the sampling distribution to know what the parameters are. It's mean and standard error. It's standard error in this case because we don't know p and we're not assuming that p is equal to a particular value for a hypothesis test. If we're using p hat to check this condition, this is going to be the standard error, not the standard deviation. The mean of this sampling distribution is just going to be p hat, right? Because that's our best estimate of p in this case, which is going to be 21 out of 122. Do I have a decimal approximation for that? I do. That's about 0.172. And the standard error, the formula for that, it's the square root of p hat times 1 minus p hat all over n, which is going to be square root of 0.172 times 1 minus 0.172, oops, all over n is 122. I believe I also have the decimal for that. That's 0.034. 0.034. Cool. So we can say p hat approximately normal 0.172, 0.034. Now, if you tried working out part A on your own, you probably didn't write all of that. If you did, wow, fantastic, great. Make sure you check your conditions, not just by checking them off, but by explaining how or why they're met. Make sure to actually state that the sampling distribution is approximately normal, and it would help to also go ahead and calculate the mean and standard error. You'll find that if you do that, you're going to save yourself some calculations later on. Part B here, we're going back to confidence intervals. It's been a minute. We want to calculate and interpret a 95% confidence interval for the true proportion of orange M&Ms in bags of 122 M&Ms. Now, in AP tests, potentially, this could be what part A says. And you would have to know to do everything we already did, as well as actually do the confidence interval stuff. All of this has to come first before any confidence interval or hypothesis test. So I don't want you to think that just because the example was made this way, that that's what you're going to see going forward. It's not obvious when it asks for something like this to do all of this work, but you do need to do it because you can't make the confidence interval unless you know what the model is. You don't know what the model is unless you check conditions. It all builds on itself. But anyway, we've already done all that work. So let's go ahead and calculate our interval. If you want to give it a shot, go ahead, pause the video, come back in a minute, and we'll see what we got. let's go. We need the formula first. Okay, so we want a 95% confidence interval for the population proportion. This is a one sample Z interval. That is going to be p hat plus or minus our critical value times the standard error of p hat. Okay. Now, the great thing about doing all of this work early is that you can write the formula this way and you don't have to recalculate the standard error of p hat. You already know what it is. We calculated that here. It's the 0.034. That makes actually constructing this interval almost trivial. So we've got this. Let's see here. The main problem here is going to be z star. We know p hat. That's 0.172. My apologies. I don't know if you can hear that in the background. There are many birds outside my office window right now. Sorry if you can hear that, and it's distracting. P hat is 0.172. The standard error is 0.034. The z star, our critical value, you might remember what z star is for a 95% confidence interval for p. If you ever forget, or if this percent is something you're not familiar with, you want a z star value such that 95% of the area under the standard normal curve is between it and negative z star. That means 2.5% is on either side here. So to figure out what this z star value is, you want all the area to the left and use inverse norm on the calculator. All the area to the left of this is 95 plus another 2.5%. That's 97.5%. And it should give you 1.96. And you may remember that that is the z star for 95%. So that's z star. So we should have everything we need to plug in here. P hat is 0.172 plus or minus. Z star is 1.96. And the standard error we already calculated is 0.034. Okay. I like calculating the margin of error, everything after the plus or minus. So I will take this product. So that's 0.172 plus or minus, that's 0.067. If you're doing this as I'm doing it and you get something slightly different, it's possible that we rounded a little differently. Rounding errors are always looked over when AP tests are being graded. If your eventual confidence interval is almost the same as the solution, but it's obvious that there was rounding error involved, you'll get full credit. That's the way it's always been. I assume that's the way it will always be. Okay. It's good to round as little as possible, and maybe I'm setting a bad example here, but if it's clear that it's just a rounding error, you'll get full credit, which is why it's so important to write every step of the process. If you go straight from here to your answer, and it's different than what they have, they don't know it's a rounding error. You might get dinged for that. So if I were doing this on an AP test, I would be writing all of this down. I'm not doing it just because I'm teaching it. Okay. This is going to be 0.105, comma 0.239. 0.105 and 0.239. So, we're done, right? Right? Oh. Calculate and interpret. Okay. So we have our calculation here. We need to interpret it. I believe several videos ago, go back in your notes, I believe there is a template that I gave you to interpret a confidence interval. And you might want to look back at that so that you know you're interpreting it correctly. Sometimes I tend to take some artistic license in my interpretation. It might be phrased slightly differently, but I've been doing this a long time. When I started, I used the template. So go back to that, write your interpretation, and we'll see how it compares to the one I write here. I think I did a pretty good job sticking to the template here. The interpretation of that interval, we are 95% confident that the true proportion of orange M&Ms in bags of 122 M&Ms is between 10.5% and 23.9%. Okay. The template, the only things that change are the percent confidence. That's based on what it asks for in the problem. You need the parameter in context. And if you ever forget what the parameter is, it should say it somewhere in the problem. Sometimes it will actually go right out and say it. I could have copied that straight from here. Okay? And then, obviously, your confidence interval endpoints should be in there as well. So, there is one more thing here. There is an... You can do this on your graphing calculator. It can calculate the confidence interval for you. I hesitate to show you how that works because I don't want you to think that it's a shortcut and that all you have to do is go beep, beep, boop into the calculator and get the answer. You need to be able to write out many of these steps to get full credit on a test. You will only want to use the calculator to check your answer, or if you forget how it works, at least you'll know what the confidence interval is, and you can try to work backwards to get a lot of these steps. I will show you how it works, but it is only to check your work or in case you're lost.
All right, so this is how to calculate the confidence interval on your calculator. So you will need to go to stat test 1 prop z. You might be able to see it. Oh, it's here. Stat test 1 prop z int. So we'll go to stat, over to test 1 prop z int. It's all the way down here. 1 prop z int. I promise it's there. You might have to go all the way down to letter A there. So that's what you need to go to. And you'll be prompted for a few different things here. And this is the case no matter how old your calculator is, I think. If you have any questions about this, let me know. I'll figure out what you need to press. But you should get a window something like this. It asks for X, N, and C level. X is the number of successes in sample. So if you go all the way, here, I've given you what each of these things is. X is the number of successes in the sample. And if you look back in your notes, there were 21 orange M&Ms in our sample. So X, the number of successes, is 21. N is the sample size, as always. There were 122 M&Ms in the bag. And the confidence level, well, C level is the confidence level as a decimal. And you can see the default here is 0.95. Generally, that's the most common confidence percentage. It could be something else like 0.9, 0.8, 0.99, but here it's 0.95. Calculate. And this is what it gives you. This is the confidence interval, and that should be pretty close to what we got. I think we got something like this. Did we get 0.105 and 0.239? We did. That's exactly what we got. So that's good. It also gives you p hat and the sample size, just in case you needed it. So, as long as you know these three things, X, N, and the confidence level, the calculator will give you what the confidence interval is. However, to show your work on a test, you need to do most of the things that we showed earlier. So, I would only use 1 prop z in here to check your answer, to make sure your confidence interval is correct. Or if you're completely lost, at the very least you can get the answer, even if you don't know exactly how you got there. Chances are, if you do that though, you'll only get partial credit. You need to show the formula for the interval, and you need to show the numbers plugged in order to get that full credit. So you can use this as a tool. I would not use it as your main source of tackling how to calculate this interval though. So that's actually it for this video. We are going to do more with this example of M&Ms. We're going to conduct a hypothesis test, but this video is long enough, so I want that to be in the next one. So we'll do that. We'll finish up the M&M's example in the next video. The video after that, we'll have a completely new example, and we'll go all the way through in one go. By then, hopefully, you're a little more confident with these confidence intervals and hypothesis tests, so that when you go out on your own to do homework and progress checks and quizzes and tests, you've got a good background. So stick around for the rest of this example in the next video, and we'll see you there. Take care.